Thank you, everybody, for joining the call or being here in person. There's a few of us. I particularly like to see real people, so that's nice. I've always enjoyed throughout my career the ability at Georgia Tech to talk to people with different sorts of backgrounds and expertise and learn from each other. And so this talk will reflect that. A lot of it is, well, it incorporates a lot of work that's been done over the years with other people that are in this call, most particularly Brook Byers, who's been pretty instrumental in helping us move this along. We'll see some work by some of Bert's former PhD students that are now in various nice places, as well as some work from some of the other people here at Georgia Tech. And my involvement is with a good deal of this, although not all of it. And, you know, because this is a pretty general audience, we'll cover a lot of ground, not always very deep, but that's always a conversation that we can have later. And I encourage you to reach out if there are things that I've said that pique your interest and you want to learn more. Biologically inspired design, which we'll talk about a lot, is an emerging field. And so there's lots of really, really interesting questions and things to discover. And we are in the early phases, right? And so what can we learn about systems from biology is part of a larger question about what we can learn about engineering and design and architecture and all kinds of other things from biology, as Michael suggested. There is a name for this field of inquiry, which, well, there's several names. I call it biologically inspired design. You might hear the term biomimetics or bionics. For our purposes, all of these are about the same, right? In that they articulate sort of a fundamental approach of using ideas and principles taken from natural systems in order to produce better human devices and technology and processes, right? And so why would we want to do this, right? Well, this idea of using natural systems capitalizes on the fact that they have a 3.8 billion year history, right, on this planet, that they have gone through a very rigorous filter, which we call natural selection, right, which eliminates all but the most very fit organisms. If you are 1% better than your cousin, that's a huge advantage in natural selection. And so the idea is that as the result of this filter, we are left with a series of really, really robust problem-solving principles that are embodied by organisms and groups of organisms. Right? Because organisms are made of the stuff of life-friendly stuff, right? It is thought, right? So I'll say this carefully, that they are inherently the principles that we get from natural systems, the materials that we can design by understanding natural systems, these things are inherently more sustainable and more efficient than potentially other sorts of uses. Now, this doesn't always have to be true, but the fact is that, again, organisms are under severe constraints. They need to be energetically efficient. They obviously need to use cheap materials. They need to use them well. And so all of this sort of a priori raises the argument that organisms do things in a way that's better than we could engineer. That turns out to be a reasonable assumption, but of course, every case is different. And so as scientists, we don't want to say things that aren't always true, right? So we'll take this as a rule of thumb rather than a law. As a biologist, one of the things that I like about this idea of using natural systems to solve human challenges is that it forces us to reevaluate the role of natural systems and our relationship to them, right? And all of us, presumably, all of us respect our teachers, right? Some of us maybe more than others, right? But if we can reframe our relationship to natural systems as one of learning from them, right, then we can reframe our relationship to natural systems as things that are aiding us in our ability to construct an efficient and just and equitable society rather than standing in the way, which is often the lens that we use to view natural systems, right? And so conserving natural systems under the sort of lens that there are opponents demands that we compromise something, right? That we don't do something that we would otherwise like to do. Reevaluating our relationship as a more collaborative one suggests that that trade-off maybe is not so important. Right? And I like that because a lot of what we do to conserve our natural systems is made really hard by this idea that they're standing in our way, that they're standing in the way of progress, that we can't do this really cool thing because, oh, look, there's a rainforest there and, you know, we need to save it, otherwise we're bad, right? That's a really bad framing and has created a lot of mischief. The other thing, which I think also is really important to me as a biologist who's worked with lots of different people and is sort of relevant to the kinds of things that you as students and some of us are engaged in, is that it requires a really collaborative approach, right? Learning from natural systems is not possible without deep engineering knowledge, without deep insight from biology, but also with a deep ability to interact with each other, right? You can't do biologically inspired design if I'm a biologist and go into my corner and Bert is an engineer that goes into his corner, and then we do our separate things, and then we magically hope that we're going to slam them together. That does not work, right? Because a lot of understanding how to do this relates to our ability to ask questions in a productive way before we find the answers. And asking those questions involves a lot of deep conversations between biologists and engineers, and that's been a really enjoyable part of my history at Georgia Tech for the last 20 years. Okay, so I've talked a little bit about biologically inspired design, sort of in general here. So let's talk about it in a more concrete fashion so that y'all can get your minds wrapped around it. All of you know what it is, even though you don't necessarily know what it is. And so I'm going to tell you a story of a man and a dog. Oops, and my notifications. And a seed. Right now, if you think for a moment about a man, a dog, and a seed, you might predict where this is going. I'll let you do that for a second. And then I'll tell you that in the 30s, I think, early 30s, late 40s, there was a man named George B. Strahl, and he was an inventor. He was Swiss and an inventor. And he was preoccupied with this particular problem as a result of two things, one of them being his wife, and the other being arthritis, right? And so his wife, of course, in the fashion of the day, had these sort of elaborate pieces of clothing that had lots of little tiny buttons or hooks on them that he would have to fasten. And that's where the arthritis comes in. Fastening those things was hard for him. And so he wanted to think of a solution to joining fabric together in a way that didn't involve fine-scale manipulation because that was difficult for him. Being Swiss, he took his dog for a walk. Comes back from his walk and he sees all these seeds that are stuck to the dog's fur, right? So hopefully all of you know where we're going here, right? And he's sitting there and he's thinking about this problem of joining fabric together, and he's, you know, picking these pesky seeds off of his dog fur, and he has that aha moment where he realizes that the thing that he's doing with the seeds are solving the problem that he has in the back of his mind. That's how we got Velcro, right? Mistral patented this idea of this sort of disordered kind of fabric that could be joined together with these tiny sort of aligned hooks. That was in the late 40s, I believe. That patent sat there for a while because nobody decided he was cool enough to be able to figure out. This is around the time that nylon was being developed. The patent was actually picked up by NASA, right? Because NASA has the same problem of trying to stick things together in an environment where fine dexterity is sort of limiting, and worked out how to sort of make this disaggregated matrix from nylon. And now we have Velcro, and you have Velcro on your body right now. I will guarantee everybody does, right? And it all came from this idea of understanding of describing a problem in a way with reference to function, that is sticking things together, and then using that sort of understanding of function to pick a system in nature that fulfilled that function in a different way and in a better way for the purposes of the design that we're talking about right now. And so that's the real essence of biologically inspired design. Understanding how to ask questions of a functional nature that allow us to find a system in nature that fulfills that function in a unique, better, more sustainable, et cetera way. Right? One of the things that's really interesting about the different toolkits that we're talking about, the natural toolkit versus the engineering toolkit, is that the natural toolkit, right, the toolkit that we get from looking at biology, solves problems using different sorts of strategies, right? And so this is from a friend and collaborator of mine, Julian Vincent, and he sort of looked at all kinds of different sort of patents and all kinds of different principles from nature to derive this, and he came to the conclusions that you see here, right? Whereas in the human realm, we often solve our problem by adding energy to it. Right? If we want to make ourselves cooler, we turn up the thermostat. That's, you know, a very coarse example, but that's sort of the way it works. We also solve a lot of problems by making very specific substances. There's over 3,000 technical materials, right, that are known, all of which have a range of material properties that we find useful, right? And between energy and substance, that accounts for sort of most of our solutions. Right? If you look at the biological world, it doesn't use energy and it doesn't use substances, right? Because those strategies are much more constrained in the biological world, right? You can't use as much energy as you want, right? If you're an animal, because if you do things more efficiently, you're going to be less fit. You can't use all kinds of different materials because that's beyond the realm of biology to manufacture, right? And again, they're expensive, right? It costs a lot to make a ceramic, right? It doesn't cost a lot to make chitin, which can be as strong as ceramic materials when they're deployed in the right way. And so this is where the idea that looking to biology allows us solutions that are in some sense better, right? And particularly better when we think about the sustainability angle. And it's very true that as we've been looking to nature, we frequently, not always, but frequently find ways of doing things that are more sustainable. So this is another really cool story. I don't see the cursor. Oh, yes, I do. Here I go. Maybe no. Okay, so the picture on the far left there is whale fin. That whale fin has those bumps. Those bumps are on the leading edge of that whale fin. No hydrodynamicist or aerodynamic person would ever want to do that, because according to the theory that we knew and now is changing, that was bad and that creates instability. But in fact, it doesn't, right? The whale has this because it increases its ability to generate lift and its ability to move effectively, and it does so by channeling the water through around those structures in a very particular way that was not easy for us to discern given our own theory. We can certainly explain it now that we know about it, but it was not something that we would have hit upon de novo, right? And it turns out that now you're starting to see these kinds of things in all kinds of human engineered devices, fans, windmills, all kinds of other things that have to move fluid, because the function of those little structures there that you see on the whale fin is to reduce drag and increase lift, and they do it very, very well. But of course, this is only one end of the range of the kinds of problems that we can solve using biologically inspired design. Credit where credit is due. Bert worked laboriously on this slide, and I shamelessly stole it from him, which is, you know, what we do, right, when we collaborate. So, for instance, we can ask biology to help us produce better sorts of materials, right? And there are lots of really good examples of that, right? And I've named a few of them, right? We can ask biology to help us design better products. And again, we just talked about that. We talked about Velcro. We talked about rail power, right? These are devices, tangible devices. I'll call them products. But of course, there are larger things out there in the real world, right? And arguably a great deal of our impact on the planet comes from these sort of larger scale things that we're doing, right? We have systems, right, that we use, right, to move these products around and to make them. And we have even larger systems that incorporates these manufacturing systems, right, into larger aggregates and interacts with the real world that we would call like cities, right? And you know, on a planetary scale, all these systems are interacting. Right, and so there's an interesting aspect to all of that, right? That biology can help us solve potentially all of these different problems, right? Or at least some of them, right? The problems that I'm interested in occur at this scale. The things that we've been talking about are the things that are occurring at this scale. And so as someone who has been doing biologically inspired design for a few years, we thought to sort of ask, well, what are we really using biologically inspired design for, right? We can use the term biomimicry if we want. Anyway, we won't worry too much about the terminology here, right? But the field is something that's maturing. It's of utility to understand the kinds of problems that we're solving using this particular approach, right? And how we're doing it, right? Because it allows us a more holistic understanding of what's going on and the possibility of making things better than they are right now, right? As a new field, there's not been a lot of inquiry about what we're really doing because we're so busy doing it. Right. So we thought to ask this question, and by we, I mean myself and a former student that was advised mostly by Brook Byers and somewhat by me, right? To sort of think about the biologically inspired design world in a larger context. You can sort of see that we went out and did what a lot of people do these days. We did a review, right? And we sort of asked lots of questions about what people were doing with biologically inspired design to figure out what we should be doing better. And some of the methodologies here, but basically we went to the literature and pulled out a bunch of articles and read them and broke them down into a series of categories. We had about 500-ish examples of this that we've identified. So most of the design goals that people use, I'm sorry, Dan, are for tangible physical objects, right? The things that we hold in our hand, right? The things that we make. And you can see the breakdown here. 60% of it are these kinds of devices, right? The other large fraction are materials, right? That we design, and together these account for a little bit, almost 3/4, right, of the questions that we're asking for biologically inspired design. Sometimes we ask things about systems, right, or networks, right, here, right? But our inquiries into other kinds of things are pretty minimal, right? And in particular, the inquiry into the kinds of systems that I'm interested in are so small that you really can't actually see them on this figure. So mostly what we do with biologically inspired design is to figure out how to make better things.
Mark, can you give some examples of network design process software?
Yes,
those
I will. Not yet. Okay, so I should turn off notifications, but I'm not too lazy. All right, so things, right? Like everything else, we're fixated on things. I'm not sure that's so great. Our designs actually also represent what I would consider to be a fairly small range of the biological strategies that are out there, right? So remember, we talked about those strategies. You'll see them again in a second. But what you should get from this particular slide is mostly what we do with biologically inspired design is to understand how shape and form and structure, and that can be at a material level or it can be at a larger level, right? To figure out how that influences design parameters, right? And obviously that's really important, right? There are only 7-ish biological macromolecules, yet to get the range of material properties that come from these 7 biological molecules are the same as the range of properties that we get with our 3,000 technical materials, right? So obviously the details of the shape and structure of those materials as they are laid down into particular design are really, really important, right? But that's not all that biology is doing. Right? It's dominated the way that we think about getting solutions from biology. So again, we're leaving a lot on the table here, right? And so again, you'll recall this is sort of the biological sort of equivalent of that structure, right? It's pretty important, right? But it's certainly not the only thing, right? Information is super important. Not a whole lot used there, and many of the other kinds of things that biological strategies are involving are not so well known, right? So again, we're missing the boat here, right? Because of the way that we think about things. This is probably the most relevant slide for the purposes of our chat here today, right? One of the things that we were really interested in, right, was where in the total product life cycle we are thinking about biology and helping that to improve what's going on, right? And so many of you have probably seen some variant of this, right? The product life cycle, right, as an engineer would imagine, right, is something that begins with the extraction of the materials that are used to make the thing, how that thing is made, right, how that thing is moved to where it needs to go, what happens when that thing is used, and then what happens when that thing is disposed, right? And so, you know, some couple of decades ago, people realized that if all you're really doing is thinking about this use phase, right, like the phone using less energy when it's used, you're missing a huge part of the amount of energy and time that's gone into this particular device, right? That starts with how much energy it costs to extract the material and ends with how much energy we leave in that device because we throw it in a landfill, right? When you toss that phone right away, right, all of that energy that's used to manufacture and move it around and stuff like that, it's embedded in that object, right? It's embedded in the materials of that object, and it can't be recovered. Right? We are only asking questions about what happens in that use phase with biologically inspired design. We can make the phone better, we can make the robot better, right? But we're not thinking about all these problems. And oh, hey, by the way, these are actually systems level problems, right? This is a system here, right? This involves systems, right? So the idea that we're only thinking about products and we're only thinking about the use phase, right? And we're only thinking about structure all sort of points to the fact that we're not thinking about the systems themselves. This also, in a way, sort of conveys the same message to me, right? And as a biologist, I'm sort of interested in where we're learning from, right? And this shows you the distribution, excuse me, of different taxa in the biological world that are used to inspire designs, right? Ranging from mammals, right, or vertebrates, I should say, which is me sitting with those super cute meerkats. Man, that was one of the most hilarious things I've ever done. Okay, you know, to insects and plants and fish and birds, right? So mostly what we do is look at mammals. I don't know, mammals are super charismatic, right? Clearly that guy in the hat is super charismatic, right? But they're actually a really small fraction of life on the planet. Right? And so are, in fact, birds and fish, right? So if we sort of look at where these solutions are relative to sort of their representation in the biological world, right, we seriously overweight kind of the organisms that are maybe most familiar to us, right? Mammals and fish and birds, right? We seriously underweight things like plants, which are super cool and have all kinds of interesting things, right? Like Velcro, right? And also insects, which, you know, are some of the most speciose groups of the planet, right? So again, we're leaving a lot on the table, right, by this bias that we have, right? And a lot of this work on mammals comes from the fact that we want to make like better robots, right? Big dog, right? Okay, so all of that basically brings us to sort of this very general conclusion that we're learning from the biological world in a much more limited way than we could. We're self-censoring ourselves with respect to the questions that we're asking and the animals that we're looking at, right? And if we really want to capitalize on this tremendous source of design knowledge, then we have to do a better job of asking questions. Go away. And we have to do a better job of interrogating the designs that are present in all these different groups, right? And so again, the problems that I'm thinking about, right, are actually problems that have to do with systems, right? And they're problems that are probably not well represented by things like meerkats. Actually, meerkats maybe. Certainly not represented by your typical mammal or bird, right? And well, actually, a lot of the things that you will see in the next 15 or 20 minutes, right, basically have to do with plants, maybe not plants, with systems of plants and animals, and with self-organizing things like insects. Things that again are not well represented in the stuff that we do. So we're back to this. We're back to this slide that we talked about, right? And we're going to sort of think about the questions that are involved here, right? And in particular, what I want to think about is how do we make more cyclic systems, right, of manufacturing and reuse, and how do we make more resilient systems, right? And I'm intentionally vague about the word system here, right? And what you'll see is that the systems that we're talking about can be sort of at the lower end here, all the way up into large-scale systems like coupled urban industrial systems, which we would plainly refer to as a city. So let's talk about that. And again, I'm going to keep things general, right, and just sort of whet your appetite, hopefully, but you know, detail we can talk about. So one of the first things to notice, right, is that natural systems use these sort of strategies that, again, have not been well represented in the kinds of things that we're doing, right? They use information and they use energy, right? That is, it's what things are flowing where, right? That is the basis of how these systems work. And that to me is information and energy. Who are you transmitting material and energy to, right? There's an information there that we can interrogate, right? And again, the very basis of these kinds of things are all material and energy transactions. At the end of the day, a complex human system, right, like a city or a collection of industry, or maybe even a single plant, is not like an ecology. It is an ecology, right? If we think about function, right? What do ecological systems do? They transfer material and energy among its components in a structured way, and they allow for the recycling and reuse of those components. That's exactly what industrial systems do. That's exactly what happens in a city. So if we get to the point where we can think of these two things as being functionally equivalent on this very basic level, right? And that's not to say that these are the only functions that cities have, or these are the only functions that ecosystems have. The fact is that equivalence allows us to understand the human city part by understanding what's going on in the ecological systems, right? And that's the central core idea here. If we understand better how ecological systems are organized, because ecological systems cycle material and energy pretty darn well, right? Otherwise they wouldn't be around. Then we can understand how to apply those lessons to things like an industry or a city. So fortunately, there's a whole branch of ecology, which in fact I didn't even know about till I came here and started thinking about this, and which actually was pioneered by people at UGA. Okay, you can boo, all right, but still, it's pretty good, right? It's a local product here, right? There's a pretty robust branch of ecological theory known as ecological network analysis, right? That attempts to sort of understand material and energy flow patterns through ecological systems, right? And how ecological systems are organized and what the consequences are. And so an ecological system, right, is composed of a food web, more or less, right? That is, the food web is this thing here, right? And it's simply a diagram of who's eating who, right? And so in this particular case, if I look here, the grass X1 is being consumed by X2, which is the grasshopper, and X2 is being consumed by X3, which is a mouse, right? Or some little rodent, right? And if you sit in my ecology class, we spend a long time talking about things like that, and the students hate it. Okay, right. But, right, there's information there in terms of the topology, right? And in terms of the flows that are going between these things, right? And the flows are simply how much of that grass is being eaten by that grasshopper, right? There are a couple of extra components here, right? There's the environment, right? There's the sun that's providing energy for the grass. There's material flows into this, right? If this is, if this is a meadow, right, by a lake, then the lake is contributing some nutrients to it, right? So there's a couple of other pools that are not represented here, right? Mostly things that are coming from the environment or going to the environment as waste, right? Which we incorporate, right? But the basic idea is that this food web, right, gives us a set of transactions that we can interrogate. Right, and we can express those transactions in a matrix, which is what's shown here, right? And that's basically a 3x3 matrix because we're only, sort of emphasizing these three species, right? Each of those species is something that is consumed potentially, right, and something that can consume, right, predator or prey, right? And so we can take this topology and express it as a matrix of ones and zeros. If all we're interested in is a link, right? So if something eats something else, there's a link there or one. And if it doesn't, there's a zero or nothing. Or we could get more elaborate, and the elements of that matrix correspond to the actual magnitude of energy or material that's flowing from one thing to another. And we can do really interesting things with both of these approaches. One is obviously a little bit easier, than another. So for instance, it's fairly easy to know who eats who, right? It's a little bit harder to figure out how much of the grass is eaten by the grasshopper, right? But those are both things that are within our capacity to do, and they're both things that are within our capacity to do for the human element, for infrastructure, right, of the human sort, a city or an industrial plant. So one of the first things we asked, and this was almost where this work started about 10 years ago with one of Dr. Browse's students, Astrid Layton. We sort of said, well, okay, there's this idea from industrial ecology out there, right, that if we put a bunch of industries together, then we have a functioning food web, and we'll do this because it's sort of more sustainable, right? And so there's some very famous examples of these industrial symbioses or eco-industrial parks or whatever you call them, and they're designed to sort of mimic, right, the circular economy, if you will, of a food web, right? But of course, they were just sort of put together. Right? I mean, this idea of waste equals food is a high-level metaphor. It doesn't really tell you much about how to do it, right? And so we wondered how much of a problem that was, right? And so we looked, right, very specifically at these things called industrial ecologies, right? Because there's quite a number of them that are out there. And we compared them to real food webs, right? And there's a bunch of stuff on this slide, but there's only two things that are relevant, right? The far left and the far right. So the far left is the eco-industrial parks, right, that we've examined. And the far right is sort of the most robust set of food webs that we can use to compare the performance of the human system with, right? And so all we did, right, was to look at a variety of these sort of structural parameters that you get by looking at the topology of a food web. And you can see that the thing on the far left is generally really different from the thing on the far right. Right? And so for every metric that we look at, the conclusion is that these things called industrial ecologies really don't resemble what we consider to be an ecology at all. They have a variety of structural features that are remarkably different, right? They don't have as many producers to consumers, right? The generality of who's being eaten and who is doing the eating, right, are much lower in our industrial systems in our human systems, meaning a given consumer in an industrial system takes material from far fewer entities, and if it's being consumed, is consumed by far fewer entities than what we find in natural systems. And that mutual dependence among actors is lower in ecological systems. So we can get all this from the topology. That affects their performance. And so this is a really good example of how this affects performance. So the thing on the left is the best performing eco-industrial park that we were able to find. But you see here that it replicates a lot of the features of systems that are in nature, right? So the green arrows represent linkages which participate in a cycle, right? And the grayed out linkages don't, right? And the red ones are particularly critical, right? Because without those, a lot of the cycling wouldn't occur, right? Those red linkages typically are taking what would otherwise be a waste and recycling back into the system. So the difference between the left and the right is really instructive, right? Each element on the left is connected to many more elements, right, in a cycle than the things on the right. So when you're participating in a cycle on the right, it's pretty much a single cycle, right? There's a single cycle right here, and there's a single cycle right here. That's it, right? If you draw all the cycles you can on this side, you'll get a whole lot more, right? And that's because, again, this pattern of connectivity is really different. As a consumer in an ecological system, you're consumed by more things. As a predator in an ecological system, you eat more things. If you replicate those features in a human system, then you get better cycling. Up to a point, right? And so designing human systems more like this, right, which is what we would consider to be more characteristic of an ecological system, should be better from a resource management standpoint, right? And in fact, it is, right? So this is some work we did with collaborators in China. Again, Bert Grass and Bert Grass's students were an integral part of that, right? As an ecologist, I can't do the engineering part, right? This is where the deep conversations can come in, right? But I can help the engineers understand where those ecological principles are relevant, right? If I can speak enough of their language and they can speak enough of mine. And so this is an industrial food web. This is the series of transactions that take place in a particular steel mill, right? And you can see that it's really, really complicated, right? But we were given the challenge of trying to make this better from a resource management standpoint. How do we make this thing use less energy, right? Or less material of any sort, right? And so we looked for those gaps, right? We looked for components that we could plug in that would hook into as many cycles as possible. Right? Because that's where the value comes in the ecological systems, right? So it's a pretty simple sort of analysis, right? I mean, it was very qualitative, right? What can we do to create more interlocking cycles? Because that's what happens in a food, right? So we're like, well, okay, if we simplify it, right? These are sort of all the nodes that we have, right? We've taken out all the flows, but if we put a wetland in there, right? That wetland can participate in two different sorts of cycles. It can participate in the water cycle and it can participate in the energy cycle. It can participate in the water cycle by taking wastewater from a variety of these processes, right, and treating them, right, and removing heavy metals, right, because plants are really good at that, right? And in fact, there are native plants, right, plants native to China where the steel mill is, that are super good for that. Now, not only does this participate in the water cycle, right, by helping to recondition the water, right, so that it can be reused more effectively, right, but we can take the biomass from that plant and we can make biochar out of it and we can use it as fuel, right? So we don't waste all of that embedded energy. And again, right, the key here is how do we plug into as many different cycles with as many different components as possible? Right. And so when we do this in silico, right, when we simulate this, we can save 10% of the energy, right, by using biochar instead of coal, and we can save 50%. We can use 50% less water, which is a huge expense in a steel mill,
right? And since steel mills contribute about 8%, I think, to the global carbon footprint, saving 10% of the energy in a steel mill is not trivial. We can even do more, right? We can apply some more explicit criteria. And this was, again, the result of a collaboration with Bert and one of Bert's students, Astrid Layton, who's continuing to do this stuff, which is super cool, right? And myself, right? And so many of you might have heard about Interface Carpets, right? It's one of the more sustainable carpet manufacturers in the United States. And that was the result of, in fact, an intentional pivot by Ray C. Anderson, who is the owner of this, right? And there's a very funny connection here. Ray C. Anderson was the reason that I became interested in this idea of biologically inspired design, right? Because Ray C. Anderson, through his foundation, invited Janine Benyus to come to talk at Georgia Tech about 20 years ago. And she talked very persuasively about how important this idea was. And I thought, well, I'm a biologist, maybe I should think about that, right? So small network kind of world. This is the Interface Carpet Manufacturing Recycling System, right? It's very, very complicated. There's a manufacturing plant. There's a series of take-back centers. There is landfills involved, right? And this system, right, allocates, and there's, of course, the county that's using these things, right? The people that are using these things, right? And so material and energy is flowing between all these different components, right? The question is, how do you optimize that network for cycling, right? And there are two ways to do that, right? One of them is the traditional engineering way, right? Which is, in this case, solved by this thing called an objective function maximization. What does that mean, right? You take every single equation that you can think of for the costs embedded in the system, right? How much it costs to manufacture this stuff, how much it costs to drive it around, how much material you get back from the recycling system, how much manpower costs, right? What's being emitted, right, through all these different processes, right? And I think for this particular objective function maximization, you had something like 17 or 20 coupled difference equations that described all those costs, right? And so what you try to do is to, it's basically a brute force simulation, right? You start altering parameters, right? And the idea is to get to the minimum for each one of those equations, right? Right, that is to minimize the difference between what's going on in your system and the minimum possible for each equation when they're not constrained by anything else. Okay, and so you're maximizing that objective function, right? Of course, there are all kinds of trade-offs, right? And so hence the simulation, right? If you drive things around a lot, you might increase the recycling, but you'll add a lot of greenhouse gases to the environment, right? So it's very information rich, and because you have to have all those costs up front, and it's very computationally expensive, right? And it's not guaranteed to get to the right solution. There's another way that we can do this, right? Which is we can take this network and we can organize it the way that an ecological system is organized. We can make that our objective function, right? That is to say, to minimize the difference between how this network is looking and what an ecological system would look like. Interestingly enough, the two things give you the same answer, right? So this on the y-axis, right, is the sort of the traditional engineering approach, right? And so the way to read this graph, right, is that the closer you are to zero, the more your system converges on that theoretically optimum objective function, right, pooled across all of those different equations. The closer you are to the left, right, is the objective function match for the biological system. And you can see they're correlated to a really high degree. When Astrid showed me this, I was amazed and she was upset because the correlations were only 0.99 something. I mean, for a biologist, that's mind-blowing, okay? And so what that means is that, for instance, if you take a look at the 6 structural metrics here, that means that if you reproduce sort of the consensus ecological structure in terms of predator to prey ratio and the number of consumers that are eaten by a particular prey species and a variety of these structural parameters that we can get, right, you automatically get to a good objective function, a good network for minimizing waste and maximizing cycling, right? You can add more complicated measures, right, that are related to the actual flow magnitude, right? So for instance, this one right here, right, gets us a little bit closer, right? Because this one here is a combination of the amount of material that's being cycled, right, which requires some knowledge of the flows, and the number of steps in a network that these substances take before they leave it, right? And so that requires more detailed knowledge, right? So, but the fact is, right, that we can get pretty good solutions by just looking at structure and make those solutions better by adding this other information. Independent of anything that we know about costs and benefits from this very engineering heavy. So we have design rules here that will allow us fairly easily and quickly to screen all kinds of different designs and to optimize them with a minimal amount of knowledge, right? And we get to really, really good solutions for designing this. Efficiency, right, in terms of the amount of cycling that's going on, right? And corresponding reductions in the amount that we're drawing from the environment or putting into the environment, are not the only kinds of things that we can think about, right? Because ecological systems are resilient, right, to change, right? We are pushing the limits of that right now, right? But historically, right, for hundreds of thousands of years, ecological systems did a pretty good job at maintaining their function in the face of some sort of perturbation, right? So how do they do that? Okay, well, there's lots of theories about it, right? But the fundamental one relates to the fact that there is redundance in the way that material can flow through an ecosystem, right? So if we're talking about material starting out at point A and ending up at point Z, right? There are lots of pathways that material starting at A can end up in Z, right? And when we talked about multiple interlocking cycles in ecological systems, right, that's a manifestation of that. If there are multiple interlocking cycles, it means there are multiple pathways for energy and material to flow through the system, right, and start in one place and end up in another, right? And so a certain amount of that redundancy, right, allows for fault tolerance, right? If we take out some subset of the organisms in the ecological system, if the redundancy is good enough, right, then material can still move through that system effectively. And so a certain amount of redundance is beneficial for a system, but there's a trade-off, right? If there's so much redundance, then the system itself can't support itself, right? Because material just goes sort of all in these different places, right? Doesn't reach certain elements in enough magnitude to support them, and so the whole system collapses, right? So the resilience of the system has to do with this balance between what I'll call efficiency and redundance, right? And so efficiency sort of is how constrained the flows are from going from point A to point Z, right? So there's only one pathway to go from point A to point Z. We have maximal constraint and minimal redundance. So this is a measure of that constraint, right? As we move along that axis to the right, our system is more constrained. And as we move up this axis, our system is more redundant, right? And so if we plot ecological systems here, they sort of operate mostly in this particular zone near this sort of peak, right? They're not over here where we find a lot of human systems, and they're not over here where we find a lot of human systems. These are over-constrained, these are under-constrained, at least from this particular perspective. So there are two questions, right? Does this curve really predict real things having to do with the resilience of a system? That would be number one, right? And number two, right, can we get systems from here or here to here by thinking about these designs? So the answer to the questions are yes and yes, right? So this is the work of one of Bert's recent students, Brian Watson, right? And he took a very engineering-y approach to the problem. He took not only a system, but a system of systems, right? Each one of these things is really, really complicated, right? And so we have a system of systems, right, that relates to paper manufacturing, right, or forest product manufacturing, right? If there's a disruption in the system, two things are going to happen, right? The system is not going to process as much material anymore because we've taken out a link, and it's going to take some time to recover, right? And so Brian essentially constructed so I need to do this. Sort of constructed a very engineering-y sort of measure of the resilience of this system, right? Which related to the amount of perturbation, right, by doing something to the system, and the time it takes the system to recover. And that's summed for each of the subsystems that are involved here, right? So the more quickly all these subsystems recover and the more functionality they regain, the more resilient this system is, right? And here you see the math, and if you want to bend your brain, you can go ahead and look at that math. The engineers in the crowd. Okay. So again, what Brian did was to, again, do this sort of simulation approach where he shuffled all these connections, right, in that particular system. And we know very clearly, because of literature, the amounts of flows that are going between these different components. And so Brian shuffled them around and added new connections where they were logical, right? And basically simulated a whole bunch of different conditions, right? I think he had 17 or 18 different ecologies here, right? And so he showed a couple, I think, what are a couple of really interesting things, right? That again, the ecological metrics track these engineering metrics, right? And so if we design systems like the ecological analogs, we'll get more resilience, right? And so these green boxes here, right, tell you where there are significant correlations between some metric that relates to resilience in the ecological network way of looking at things versus this system of systems metric that Brian has derived for this system, which is on the y-axis, right? And so all those green boxes show correlations, right? And so there are a couple of really interesting ones to me, right? I'm going to point out this one right here, right? This is the correlation between robustness as measured by ecologists and system of system resilience as measured by an engineer. And you can see they're well correlated with each other, right? So a system that's constructed to be resilient from an ecological standpoint, using that curve I showed you, is resilient from this sort of engineering standpoint. This one is very interesting to me too, right? Overhead is the unused capacity of a system, right? It's related to redundance, right? So if a system, so if a system is very redundant, it also has a lot of excess capacity to move things around should a link be just removed, right? That tracks system of system resilience, at least within the simulation parameters that we've developed here, right? This is something called average mutual information. It's a measure of constraint. When average mutual information between components is high, they're only talking to each other. Again, this is not what ecological systems do, right? That creates a brittle system, right? The higher the AMI is, right, which is a network-wide measure, right, the lower our resilience is. So again, we can take an ecological principle of how to create resilience, and we can transfer it to the human domain, right? This shows you a little bit more elaborate approach to this in a system that's that's a real system, right? That is again back to this idea of can we sort of intervene in industries to make their industrial symbiosis or eco-industrial park formulations more resilient, right? And it'll show some other things as well, right? So this is back to this quote unquote really, really good industrial symbiosis that turned out not to be so good when we analyzed it, right? But it's got a water network in there that you can see, right? And so the question is, if we use ecological robustness, right? That parameter R that I showed you, right? As a design criteria, will we get a system, again, that's more fault tolerant from an engineering standpoint? Right? And so what Astrid did, basically, and this is the student that Bert and I had that sort of started all this work, right, was to essentially use this objective function maximization approach, again, to design a system to maximize R, that robustness, right? And she combined that with a cost function, right? So her objective function pays attention to robustness, shown here, right, with the target of putting it right here, right, while at the same time minimizing the cost of the water system. So it's really interesting, right? Here is the model that's based just on cost minimization, right? It's okay, right, from a resilience standpoint, okay? But it's not great, right? Here are the two bio-inspired solutions to how to construct this network. And the difference here is how strongly you relate that robustness function in your approach, right? If you weight it really strongly, you get this. And if you weight it a little bit less strongly, right, then the cost function turns out to be more important and you get this. Both of these still are better than this. Not only are they better from a resilience standpoint, but they're better from a recycling standpoint. Each one of these systems recycles more water than this one does. The best one, right, which is the one at the top of the curve, recycles twice as much water. The other one recycles about 10% more water. That's not trivial, but that's not great. Right? Now, what about cost, right? The cost involved here in this function, right, is only the cost to maintaining the network as it is. But if there's a fault, the cost of the human engineered system, right, the one based on only cost minimization, is paradoxically way more expensive, right? So what happens if there's a fault, right? So there are various fault scenarios that we could put in here. A pipe bursting in various places, right? Or one of the critical nodes going down, right? All those are faults, right? So it turns out, right, that the cost of a fault is way worse, right, for all of the human systems that are designed to minimize operating costs. So if you add the total cost together, the biologically inspired system is superior, right? So it minimizes the overall cost if you assume that there's going to be some fault sometime. It helps recycling. It increases resilience. So this is about the last slide, and I wanted to get to it only because Beryl asked a question, right? So it turns out that there are humans involved in lots of these things, right? And so human behavior is is sort of a wild card here, and people don't quite know how to deal with it, right? Or they do, but the approaches are maybe wanting, right? Turns out that there are lots of really interesting aspects of self-organization in animal systems, right? And some of the ways that animals create self-organized behavior are shown here. All of these can be mapped onto human systems in some way, allowing for the possibility that understanding how organisms behave in self-organized systems can make our own systems more efficient and more resilient. And I'll show you very briefly an example of this, right, which is from one of my colleagues at Georgia Tech, right, who realized that the way that honeybee colonies self-organize their own behavior to efficiently get pollen from widely ranging sources of flowers turns out to be the best way to design an algorithm to allocate servers to internet devices, right? So there's really one important thing there's two important things about the way that bees do things, right? There's no central computer here, right? So every bee is acting independently based on its own local knowledge and experience. Right? that local knowledge, right, has feedback rules to it and feed forward rules to it, right? So some aspects of the information that's acquired by the bees locally, based on their activities and what's going around them, amplifies certain behaviors, and in other times it represses those behaviors. So at the end of the day, what a bee does is it goes to the nest and it sees all these different scouts, right, that have found a flower patch and they're dancing. The better the flower patch is, the more dancing there is, the longer the dancing there is, and the more bees are paying attention to it, right? So that's local knowledge, right? And there's a positive feedback there, right? Honeybee goes in there, sees all these bees dancing, sees them dancing vigorously, so goes, oh, that's a really super good patch. I'm going to go to it too. The other thing the bee pays attention to is the amount of time it takes the bee to have its pollen offloaded once it comes back, right? And so it goes to that same spot, right, that it started, right, with all these bees dancing. And if there are lots of bees that have done the same thing, then it takes a long time to get its pollen unloaded, right? And if that time increment is too long, the bee goes, screw that, I'm going to go to a different patch, right? So those two rules, there's one other rule, right, which relates to the fact that bees sometimes randomly decide just to go explore somewhere, right, to find new patches, right? And there's a threshold that causes that to happen, right? Those three rules together explain almost everything you need to know about how the honeybee colony efficiently extracts information. And no central computation, all the information is freely transmitted to the environment. There's positive and negative feedback. You put those two things together in the right way, you get a really, really good computer algorithm, right? And so this shows you the parallels between the two systems, right? Because if two systems are doing this, functionally doing the same thing, then you can borrow from one to the other, right? Again, that's everything that we've talked about, right? And so you can create lots of functional parallels there. And so you can institute what the bee does, right, as a server algorithm for how to decide, you know, how to allocate server time to Amazon versus Netflix versus something else, right? Because the problem is the same. The server doesn't want to sit around empty, right? But if you put too many servers onto one thing, then somebody else is going to get neglected, right? It's the same thing that's going on in a bee colony, right? Turns out, right, that this is 10 to 30% better than the sort of traditional ways that people have done this in the past, right? And it's really, really, and it gets better as conditions get more unpredictable, right? It's robust. All right. So Aldo Leopold was a great ecologist. He was one of the first guys to realize that if you kill all the wolves, right, you're probably going to have a big problem with deer, right? You know, he said that, and then they basically fired, right? So his advice was to think like a mountain, right? My advice was to design systems like nature. And so with that little nugget, I will call time.
Yeah, thank you.
Thank you. We're over time, but maybe we can have a question or two. If we'd like, maybe one in the room and then maybe one online if there is any. If you want to unmute and present yourself at some point. Anything in the room?
Dan.
What are you working on next?
Yeah.
Dan asked, what am I working on next? You know, I'm not sure at the moment. There's a couple of possibilities. We really want to apply it, right? I think we've gotten to the point where we understand enough about how to do it, right? And we need some real use cases. Unfortunately for that, I need people like engineers.
So one use case that occurred to me while you were talking about is how we think about diversity in energy systems, right? So trade-off between getting low prices versus having resilient systems that have lots of energy sources.
Energy is a good one. There's some work on that. The diversity issue is always a hard one, right? Diversity isn't always good, right? There's a limit to how much diversity is good. I'd like to get to some more implementable design rules, right? So that you could give them to a designer and you say, okay, so when you're going to actually design a system of this, follow these steps, right? Because if it's too hard, people aren't going to do it, right?
And we've done a little bit of work with industry to try to put it into a framework that they can occupy, that they can sort of use. That's a tough go, but we have to be able to do that in order to make this relevant. The other part about it, I think that's hard that again, I think I would like a good use case for is how to deal with the physicality of some of these systems, right? So in some of these systems, right, we're designing the network as if there's no distance between them where bad things can happen, right? And so again, that's actually a real sort of real world design problem, right? It's like, yeah, you can put these components in, in a city, it's easy to imagine how you can network these things up. But if they're at the end of town, right, then how do you sort of deal with that in a networky kind of approach, right? So because we don't worry about that when we're talking about species, but because they all run around everywhere, so we assume that that's always going to be possible. And if you're online and want to ask something, unmute. All right, well.
Let me ask. Oh,
Okay.
I have one. In your literature review, did you get any sort of sense of what domains of human activity there might be low-hanging fruit? So you did steel. If you broke human activity out in a broad range of things, built environment, agricultural systems, transportation, those types of things, is there low-hanging fruit?
That's a really, really hard question. So I'll give you a general answer, right? Because I don't know enough about the world at large to be able to give you a specific case. But the general idea is this, right? So one of the things that I think is true from our understanding of evolution, right, is that the more constrained a system is, right, the more evolutionary baggage a system has, the harder it is to change it, right? And so, for instance, we're never going to get rid of our appendix, right? Why are we not going to get rid of our appendix? Well, one reason is it doesn't cost us a lot to carry it around, right? But even if it did, it'd be really hard to get rid of because when things develop so early on in our developmental trajectory, everything else that happens is going to get mucked up, right? If you try to change that, right? And so think about cars, right? There are a ridiculous number of steps to go into manufacturing a car, right? There's a capital investment for an auto plant, right? And those auto plants don't recover that capital investment for 30 years, right? And so to say, well, no, if you did this with your auto plant, right, to change that, then you could get a better, a manufacturing system. A lot of times people are going to just say no, right? Because they put so much energy into it that and their time frame, right, is insufficient to allow them to sort of think about the costs in a larger framework, right? And so the more constrained things are by manufacturing and by these kinds of things, the harder it's going to be to intervene in them, right? And so, right. And so that's where progress is really, really, really difficult, right? Sometimes we can do things that provide really great benchtop solutions, but are really difficult to scale up because the manufacturing systems, nobody will want to develop, right? And we've had that a number of times happen with industry.
You mind if I pipe in a little bit, Mark? It's Bert.
Bert, come on, man. That's the hard one.
No, as I said, answer that because the low-hanging fruit, I would say, like, we wrote a proposal that the auxiliary systems in manufacturing, what we worked on the water, connected to agriculture, those are potentially low-hanging fruits that you could easily say, okay, that's outside the classical manufacturing, outside the classical domain. Why don't you try this? That's what I would call low-hanging fruit.
Right. A better, more exact way to answer than my vague stuff. And anybody else? Thank you, Bert. All right. Well, thank you, everybody, for your attention. If you're online, hopefully it was interesting enough to keep you occupied.